Welcome back.
We're here. We're back.
We're here for a magnetic talk with you.
Oh, hey, there you go. I like that.
So today we're talking about electromagnetism.
Magnetism.
Yeah, it is one of the fundamental forces of the universe, and it's way stronger than gravity. And
Holds planets.
it's what holds matter together.
Yeah.
So it's a fascinating topic. It has a lot of depth to it.
Deep. Yeah,
We're going to get through just a little bit of this here, just a
touch the
tiny
crust.
bit
We're touching the
of this
crust on
here.
this one.
But kind of want to introduce you to the topic and make sure that you fully understand that. So electromagnetism is making electricity using electrical current. Electromagnetic induction is when you're making electrical current using magnetism. They are one and the same thing. This is the fundamental force of nature. But what it means is that, and we talked about this when we talked about induction already, magnetism is generated anytime current is flowing through a wire. And that field increases and decreases with current, long and short of it. If we have a wire and we send current through it, we generate a magnetic field. The more current, the stronger the field.
Yeah, kind of like what we see with solenoids, right?
Yeah, with solenoids. If we double the wires in a given area, that's going to make for a stronger magnetic field. And we can build very strong magnets by coiling wires up.
You can make a bigger solenoid.
Yeah. So when we were talking about inductors, we were talking more about how they perform as part of a circuit.
Mm-hmm.
Here we're talking about how the magnet part of it actually plays into it. So let's hit the next slide here. Here is what we would look at if we were looking at a cross section of a coil. So if we sliced a coil in half, what we're looking at here, the little dots and the pluses with the circles on them, those are the cross sections of the wires that we would see. So essentially this is a coil that is looping back on itself in a spiral fashion. And so there's a magnetic field that's generated around each one of those wires, and it goes like that. And the cool thing about it is that when we're dealing with this, you can see that like the current is flowing in one direction, coming out at us on one side, and then it's going back in on the other side. So that's why the rotation is different on both of those. And as a result, it accelerates it. It acts as magnetic field conveyors, basically.
That's a good way to put it.
Yeah, it's little conveyor rollers on them that are essentially accelerating the magnetic field and making a larger magnetic field with that. And that's what you see here. Those larger oval rings there, those are pointing you at a larger magnetic field being generated from all these tiny little roller magnetic fields.
Very cool.
So we coil that up, and coiled shapes are called solenoid shapes. That's why we call solenoids solenoids. Yeah. Hey, you knew this before you knew it.
Yeah, there
right?
you go. You're welcome.
You're welcome. We gave you lots of spoilers. And so the more loops that we have, the stronger we have concentrated that magnetic field, right? And if we place a ferromagnetic core inside of it, it magnifies the strength even further. So essentially what it winds up being is that each wire is parallel to another wire flowing in the same direction, and those will attract one another. And then wires that have an opposite reaction, they will repel one another with the magnetic field.
That's similar to when you take a north and south magnet and you polar opposite.
Yep.
And what happens?
Yep. And then magnetic fields had the effect of forcing electrons to move, creating current. And that is EMF, that's electromotive force. And that varies with the time, the change in current, and the geometry of that field as we generate that with both a core and with the number of windings around that.
Left and right hand rule.
Left and right hand rule. So let's talk a little bit about that whole thing there, right? When you're looking at conventional current, so keep in mind that's not the actual electron flow. That's what Ben Franklin made that mistake way back in the day. When you're talking about conventional current, you use the right hand rule, which means you take your right hand. And this actually probably, yeah, this is my right hand, even if the screenshot is mirrored.
Yeah.
But yeah, you can see both of us doing this dance. So if current is flowing in this direction, the magnetic field curls like this, which is super fun. And then if we're talking about the direction of current, and you can check this out, I can hold my hand this way and hold my hand this way. You can see my thumbs are pointing in opposite direction. So my left hand my thumb is pointing in the direction of actual electron flow, and see we get the same curling motion here. And you can start playing Thriller whenever you want. Thriller.
Halloween coming up.
Halloween coming up, you know.
Definitely appropriate.
I don't know how long people remember the Thriller dance from, but
I'm sure
they play it enough.
Yeah, they do.
But yeah, so that's what it is. The right hand and the left hand rule, and that's why those work. So right hand, conventional current; left hand, actual electron flow. So if we relate that, actually, let's go back a couple of slides there just to kind of relate that to what we see here on the screen there. We've got conventional current, and we can see that it's rotating that way because the conventional current on the left-hand side is coming out of the screen, whereas conventional current is going towards the positive on that side of the screen. So if I do that way, the right-hand rule applies. And likewise, if I do it with my left hand, we're showing actual electron flows. Electrons are flowing away from the positive side. That curls the right way. And then over here on that side, the electrons are going back into the screen. And that works that way.
Yeah.
So
we're going to expect you guys to have these hand gestures down by the next
yeah,
class.
like if you can't do a dance off with us, what can we really expect of you as students? Like,
I agree.
So yeah, let's go back forward just to kind of tie the knot on that one. What else do we have?
That was it on left hand, right hand, and electromagnetism. So
Okay, so motors. They work by manipulating these two fundamental principles of electromagnetism. The first being that two magnetic fields of the same polarity will repel from each other. They'll drive each other apart. And
north, south, and south.
Yeah. And two magnetic fields of the opposite polarity will attract one another. So all we need to do is we need to get, to get a rotation is to get one set of magnets to repel each other and one set to attract each other, and then we can shift the rotor inside of a motor. So let's take a look at these phenomena in action. So here's a magnet interacting with another magnet. You can see it's attracted to that magnet, and when we move that magnet, it is
looking for it.
It is looking for it. It's attracted to it. It's pulling it around. And then you'll notice that the magnet was then flipped, and now it's repelling. Sometimes attracting, and it just depends on which side of the magnet we're presenting to the other magnet. So you can see the repelling action and the attractive force. Okay. Let's hit so that's the magnetic side of thing. Induction is the other side of it. That's where we're using magnets to create voltage and current in a conductor. So let's see what happens with induction. So here we've got a coil of wires, and we're waving a big magnet over the top of it. And it doesn't produce much here because there's not a whole lot of wires. but you can see that it is producing voltage, and it's going back and forth between positive and negative as the movement changes over that coil of wires. So when current is induced, we create a magnetic field in that conductor according to the Lorentz force, which is that left-hand, right-hand rule. The polarity of this field can be manipulated by changing the direction of that current, which, you know, yeah, we get it. Just change the current, you're changing which side of the dance you're doing.
There you go. You guys get it down.
Make sure you get it down. And north becomes south, south becomes north when we change that polarity.
Yep.
So pretty easy. That's what's happening when we create a magnetic field using electricity. Here we go. This is a fun one. So if the electricity has nowhere to go but to heat things up, this is called an inductive heating. So this is a current that's flowing through that copper coil there, is actually inducing heat onto that metal rod that we're putting through there. And you can use this to melt metal with.
You can.
You may have heard of induction cooktops for your kitchen.
Yep.
That's what it's doing. That's why you need a metal pan on it. It won't feel hot to touch.
No.
It will only feel hot when you put something metal on it. It's inducing heat in there.
Yeah, those are actually pretty cool. I've seen some that just look like granite countertops.
Yeah.
They don't even look like they have
Yeah.
stove on top. And
Yeah.
they're actual cooktops.
They're actual cooktops, and you can put your hand on it and it's on, and it doesn't do anything unless you're wearing like an aluminum ring or something like that. Then you got some problems. Then you're going to have a nice little burn. But yeah, this is an effect of induction right here.
Very useful tool.
Very useful tool. Now,
Rabbit hole.
holy crap, there's a lot to this. This is one of the fundamental forces of the universe, right? So the effects of it as we move through different scales, whether that be cosmic scale or down onto like subatomic particle scale, there's tons of rabbit holes around it.
Huge range of this.
It affects so much. You know, everything from chemical reactions to slot cars to anything that works in the real world, you know, has some sort of element to it of electromagnetism.
Knowing that this exists and it's everywhere is important to account for.
Yeah. You could spend the rest of your life going down this rabbit hole. There are people that do that.
We're not doing that here.
But that's not what we're here for. We're really going to focus solely on deepening our understanding of how motors work and how AC transmission work. So like we don't need to dive.
That's a deep enough hole as it is.
That is already a deep enough hole. So we're gonna size that out for you. We're gonna just say like, okay, we're not going to get into these things. These other things exist. Honestly, like neither of us are qualified to talk about much else besides motors and AC.
Yeah, you guys are more than welcome on break to dive into this stuff and
there's a long amount of YouTube that you could go through and learn a whole lot. You know, but yeah, like for our class, we're gonna stay in our lane.
I agree. All right.
All right. Well, I think that's all we've got for this video, right?
That is.
Yeah. Let's call it, and we'll see you in the next video.
We'll see you guys later.